In this final video of Chapter 13, we're going to talk about some synthesis strategies that are specific to epoxides. So the first thing to look out for to know that we may be using an epoxide intermediate is if we're installing two functional groups on adjacent carbon atoms. Right, when we open up an epoxide, we're going to get the alcohol, and then we're going to get the nucleophile that we added. So whenever we see two adjacent functional groups in the product, there's a pretty good chance that we went through an epoxide. So in this case, we started with an alkene. If we convert that into an epoxide with peroxy acid, then open that up with a nucleophile, we can get an OH and another functional group on adjacent carbon atoms. So whenever you see this pattern, you probably want to think that we're going through an epoxide intermediate. Another thing that we can do with epoxides is by reacting them with Grignard reagents, we can modify the carbon skeleton. And so in reactions that we saw before in the epoxide opening reactions, if we react this with a Grignard reagent and then follow it up with a water workup, we can open up that epoxide by adding the alkyl group as a nucleophile to my epoxide. Now, in the examples that we've seen in this chapter so far, generally we're starting with an epoxide and then opening that up. Very often in synthesis, it's really helpful to sort of think about it backwards, right? Rather than starting with an epoxide and then reacting that with a Grignard reagent that we made from an alkyl halide, oftentimes it's very useful to, if we're starting with an alkyl halide, we can then convert that into a Grignard reagent and then react that with an epoxide as a reactant. Now, we've already seen last chapter how I can use Grignard reagents to modify my carbon skeleton. And the reaction that we learned last chapter was, let's say I have an alkyl halide. I then react that with magnesium to turn it into a Grignard reagent. If I then react that with an aldehyde, the Grignard reagent will attack here, and I'll install these additional carbons onto my initial alkyl group. But the OH is going to be on the first carbon of the newly installed carbon chain. Right? Alternatively, if I do sort of the same process, but rather than react it with an aldehyde, if instead I use an epoxide, so let's imagine we've already converted our alkyl halide into a Grignard reagent. When I then react this with an epoxide, and so the R group is going to attack one of the carbons on the epoxide, then that's going to open up the epoxide, and the OH is going to end up on the second carbon of the newly installed carbon chain. So this is a big difference between when I use an aldehyde with a Grignard reagent versus an epoxide with a Grignard reagent. I can change where the functional group ends up, which can be very useful in different syntheses. So let's look at a couple examples. In each case, we want to propose an efficient synthesis to achieve the given transformation. So it's always good to check and see, did our carbon skeleton change? And in this case, obviously, it did. Right? And so we're installing 3 new carbons, right? But the OH is on the second carbon of the newly installed carbon chain, right? So this probably tells me that I want to go through an epoxide. So if I turn my alkyl halide into a Grignard reagent, I can then react that with an epoxide. And so in my epoxide, right, these are the 2 carbons that are part of the ring, right? But then I'm going to need one additional carbon atom coming off that ring. So the epoxide that I want to react that with is this one, right? And so my nucleophile is going to attack here. It's going to open up the ring. And so I've installed my phenyl group on the first carbon. The OH ends up on the second carbon. And then to finish this off, whenever we have these Grignard reactions, I always need to finish it up with a water workup. Okay, so this is a similar synthesis, right? The difference is, in the last case, the OH ended up on the second carbon of the newly installed carbon chain, where in this case, the OH is ending up on the first carbon. So the idea is the same. Convert this into a Grignard reagent. I'm going to draw this slightly differently, just as an alternate way of drawing the Grignard reagent. Right, we can sort of think about, we have the alkyl anion, right, and then the NGBr. In the last case, when I wanted the OH on the second carbon of the newly installed carbon chain, I used an epoxide. If I want the OH on the first carbon, then in this case, I'm going to want to use an aldehyde. Right, and so now my nucleophile is going to attack here, and so the OH is going to be on the first carbon of the newly installed carbon chain. Right, but as before, I need to finish it up with the water workup. Okay, one more example. In this case, when I check my carbon chain, I see that it has not been modified, right? But what I do notice is I have two functional groups that I've installed on neighboring carbon atoms, right? So this is another indication that I'm probably going to want to go through an epoxide, right? And so the epoxide that I would have come from, sort of think about working backwards here, right? If I start with this epoxide, because these ring opening reactions are always SN2 mechanisms, right? If I attack here with the SH, right, that's going to invert the configuration, and that's going to convert the methyl from the dash into the wedge that I have in my product. Now, we need to be careful with the regiochemistry, right? If I use NaSH, then SH minus is my nucleophile, and when I have a strong nucleophile, which I would have with SH minus, that's going to attack always on the less substituted carbon, right? So it's going to attack here. So if I used NaSH, the sulfur is going to go here, and then the OH is going to end up on the same position as the methyl group, right? And that's obviously not what happened, right? But if I use acidic conditions and use sulfuric acid with H2S, right? H2S is a weak nucleophile, and under acidic conditions, right, if I have a tertiary carbon that's part of the epoxide, under the acidic conditions, it's going to attack there. And so what I want to use is sulfuric acid to give me my acidic conditions, and then H2S is going to install it on the more substituted carbon. Okay, so I know how to get from this epoxide to my final product, so now I need to get from this thing into an epoxide. So if I sort of think about working forward, right, when you see a compound that doesn't have any functional groups, generally we need to start with radical halogenation, right? That's about the only way we know to turn this pure alkane into something with a functional group. So if I react that with Br2 in the presence of light, that will put a bromine atom on the more substituted position. All right, I know that to make epoxides, we usually start with alkenes, so I want to convert this thing into an alkene. Now, the leaving group, the bromine, is on a tertiary carbon, so any strong base will give me an E2 reaction, so I'm going to use NaOET. That will give me this alkene. So I know how to convert an alkene into an epoxide. I can use a peroxy acid. I'm going to use MCPBA. And then because we can create the epoxide on either side of the double bond, I'm actually going to get a racemic mixture. So I'll get both the compound here I've drawn plus the enantiomer. And so then when I open up that epoxide, I'll get this compound and its enantiomer. All right, so I'd really recommend for synthesis, It really takes a lot of practice, so please don't neglect to work the homework synthesis problems from the lesson plan.